Hi, everybody. Good afternoon. I'm Chen Goldberg, and here with me is Robert Bailey, and both of us are from the engineering team at Google working on Kubernetes project and Google Container Engine. We are very happy to be here, and today we'll be talking on how to run your production workloads in containers. So containers has taken off because of the benefits in developer productivity. The ability to start from development environment and take the same image to production can be a game changer, right? The ability to push changes quickly and as many as you want in a day can change everything, and you can really respond to business demand. We have an example from one of our customers, one of our Google Container Engine customers, Porsche, for example, and they are able to deploy from commit to production in less than 10 minutes. They are doing it between 30 to 50 times a day. I'm sure many of you already know that and find that very appealing. We, in Google, know it for a very long time. We've been using containers for over 12 years now. Everything you know, right? If it's search or maps, even Google Cloud Platform, our VMs run in containers. We believe that running in containers is the best experience, both for developers, but also from operational perspective. Using containers and container orchestration, we were able to grow our fleet 10 times faster than growing our operations team. Now, with Kubernetes, and Google Container Engine, we would like to give a Google-like experience for all of our cloud users. So what does it mean running at scale in production? Right? It's very different than before. How do you adjust the quality of service to different types of applications that have different requirements? How do you make sure that every service or application doesn't hurt other applications and vice versa? If you really want to grow your fleet much faster than your ops team, you need to automatically monitor and remediate applications and machines that are failing. Production changes everything. And there's another truth that is different than the way we at Google run. You are not running in one place. I'm sure all of us would like to start from scratch every time we need to choose a different platform, right? Stop everything, and we are starting to write all new code. It doesn't work like that. Most production workloads have some dependencies in existing services, some of them running on-premise, in cloud, multiple cloud. This means that you need a stack that can support you running your containers everywhere you want. We believe you need to have the freedom to choose based on the merit of the underlying cloud where you want to run your applications. And we want to meet you where you are, meaning that if you are now running on-premise, we want to make sure that we are able to support you in your journey to the cloud. So a good place to start is with Kubernetes. Kubernetes is an open source project, a container-centric infrastructure founded by Google in 2014. It's based on all of our years of experience running containers. When we started with Google Cloud Platform, we thought to ourselves, should we provide something similar to what we have internally to run our own containers to our users? The obvious answer was yes, but the team insisted it would be open source. You can imagine it was a hard pitch to make, to take something that differentiated us until that day and make it open source, available to everybody. So why open source? First of all, as developers, we all prefer open source. We like the credibility, knowing what inside, how the code looks like, knowing the developers, having visibility to the roadmap. It also provides us flexibility. So if you would like to change things that will meet our need, we are able to do that. We can integrate different types of tools. And for us as an engineering team, we needed that immediate feedback loop. So we knew how we are running production, and we knew how we are running Google applications, but we didn't know much about how everybody else are doing that. And that was really important. So by building a community around our open source project, we were able to get feedback from partners, customers, and just individual contributors. We have taken it seriously, and we have donated Kubernetes to the Cloud Native Compute Foundation. And we are also building programs to help users make informed decisions of which people with whom they should partner and where they should put their workloads. Managing a community takes a lot of effort, and we invest a lot in that. So as much as we invest in the technology, we also invest in helping partners and users, wherever they are, use and leverage Kubernetes. And I think we're doing a good job at that. Looking at the Kubernetes community, you can see a lot of names. Some of them are speaking in this conference, like Sam from Box. And what I like about this community, that not only people are adopting, both contributors, both vendors and users are contributing back. So if Kubernetes is so amazing, it's an open source technology and everybody can use it, then why do you need Google Container Engine? So first of all, yes, it is pure Kubernetes, and we are very proud of that. Kubernetes is a very good tool to automate the deployment and scheduling and management of your containerized applications. On top of that, we are bringing our own experience, a year of experience, to manage your cluster. And we do all of that on top of Google Cloud Platform with the best network, persistent disk, amazing performance, and such features on Google Cloud Platform. This provides for you the best platform to manage your applications, instead of focusing on the machine and the infrastructure. And of course, running in production means worldwide at scale. You can see this is our current regions and, of course, the future regions, so we keep expanding the reach of Google Cloud Platform. So how can I convince you that this is ready and the technology is ready to run your production workloads? I think the best way to do it is just to use by real customer examples. And Niantic was a big story for us, very exciting last year. They chose Google Container Engine for its ability to orchestrate their containers cluster at planetary scale. What was interesting about it, when they thought about planetary scale, when they planned everything, they missed what actually planetary scale is. And we can see what they thought will be the target traffic, what they planned for, right? So they planned 5 times worse than that, and then we can see what was the actual traffic. And for us, this was also amazing. Because something that you get when you are a Google Container Engine user, you get us as part of your team, right? And I think this is one of the biggest value when you are working on Google Cloud Platform. You get Google as your SRE. SRE stands for Site Reliability Engineers. Today, when we manage our production systems, we have dedicated teams that are responsible for managing those production applications for Google and for our customers. And this is not about monitoring and recovering your system. It's about continuously improving the production, creating more tools, more monitoring solutions, more automation to make sure that everything is working better all the time. And when you are a Google Container Engine user, you benefit from that. So going back to the Niantic story, when they saw the traffic is much better than what they expected, we just gathered the team together, right? And we had people from support, from Niantic, of course, SRE and engineering team working together and making sure that players can continue and play and find Pokemons. So what do you get when you start a cluster on Google Container Engine? The first thing we'll do, so it takes about on every 3 minutes, and we will provision your cluster, and you will get a control plane, which we will manage for you on your behalf. And from a user perspective, you get a black box API endpoint, and we take control of all of that. But the main benefit is not about the provisioning of the cluster, but the way that we manage everything for you. So we make sure the control plane is up to date, and we upgrade to the latest Kubernetes version. We monitor it. We make sure it's available. We make sure we have backups. We make sure backups are working, right? That's something that sometimes we forget to do. And we also provision your VMs. But when we do that, we not just take this standard Kubernetes version, but we also add some add-ons that are required to run production workloads. If, for example, you need an L7 load balancer or FluentD for monitoring and your dashboard, we make sure that everything is available and you can immediately start deploying your application instead of worrying for cluster configuration. I'm also happy to announce that we just expanded our responsibility, and now we are not just responsible for your control plane, we also do VM auto repair and auto upgrade. This means that we update Kubernetes to the latest version, we monitor and automatic repair. It's now available on beta, and I encourage you all to opt in onto those features. This means that you get all the innovation coming from Kubernetes, which if it's new features or security fixes, all in a reliable manner. Now let me hand over to Robert, and he will talk about autoscaling.
Thanks, Ed. So one common problem that application developers face is how to handle traffic fluctuation. Some applications have a sort of predictable diurnal cycle of traffic, while other applications, such as the one by GroupBy, have large spikes during holiday seasons when you might see a lot of people purchasing on Black Friday or leading up to Christmas. As an application developer, you should not need to worry about constantly tuning your application. Google Container Engine can take care of that and scale the number of VMs in your cluster and the number of pods that are serving your application. So first, a bit of background. I just mentioned pods. What is a pod? Some of you are probably very familiar with Kubernetes, and for others, this may be something new for you. A pod is a small group of containers. It's not a one-to-one mapping with containers, it's one or more containers. And this is actually a very important distinction because there are a lot of times when you want to build an application where two things need to work very closely together. A pod is also the atomic unit of scheduling. When you want to schedule your application to run in your cluster, it gets scheduled with pods being co-located. Pods share an IP address, they share local disk, they share local IPC. And so a good example of this is if you wanted to launch a simple web server. You might have a custom application that knows how to pull your website content from GitHub or from a cloud storage bucket or from a local on-prem version control system. And you can pair that with sort of an off-the-shelf generic web server like Apache or Nginx. By putting these two containers together, you are then able to deploy them as a single unit where the data puller can write to the local disk and the web server can serve off the local disk. The great thing about this is that it decouples the application development lifecycle for the two pieces of code. You can push new versions of the web server if there's a security fix without having to rebuild your application, and vice versa. You can update your application without having to rebuild the web server. So now imagine you're running your small website, and it starts to get popular. So you could, quite easily with Kubernetes, scale the number of replicas or number of copies of your website that are running. You could start out with 1, go to 2, go to 4. And easily handle the traffic load. But you probably don't want to spend all of your time constantly changing the number of replicas of your website that are running. That sounds kind of boring. You want to spend your time building new websites. So what you can do is you can turn on horizontal pod autoscaling, which will monitor the incoming request load and the utilization of your pods and automatically scale the number of pods for you. It'll actually also scale down if the traffic to your website goes down as well. So you're not actually using extra resources. So this is great. So the number of pods keeps increasing. But now let's say your website gets really popular, and the number of VMs that you have in your cluster is no longer sufficient to run all of the replicas you need for your site. You can also enable a cluster autoscaler. And a cluster autoscaler will look at the unschedulable pods that you've requested, you or automation has requested to run in your cluster, and will provision new VMs for you to allow those pods to run. And it's actually smart enough if you have a cluster with different types and shapes of VMs to provision the right type of VM for your pod to run, because it runs a simulation of if I add a new machine type, will the pod actually run? And doesn't add VMs needlessly when it won't actually help you scale your cluster up. Like horizontal pod autoscaling, will scale your cluster down when the extra VMs are no longer needed. So if you have a big traffic spike, say for the holidays, and then traffic goes back to sort of a normal level after the holiday event is over, you don't have to go and deprovision VMs to save yourself money. The cluster autoscaler will do that for you automatically. One of the great things about working on both Google Container Engine and Kubernetes is that we often find cases where we can solve a problem for our Google Container Engine users and also for the community at large. The cluster autoscaler is a great example of this because we recognize that this was a problem that we had for our paying Google Container Engine users, but it was also a problem for anyone who wants to run Kubernetes. So in this case, what we did is instead of writing a proprietary cluster autoscaler that would only work with Google Container Engine, we actually wrote the cluster autoscaler as a pod that you can run in any Kubernetes deployment. So it runs just like any other pod, and it talks to the Kubernetes API to figure out when it should scale up. And our implementation then uses GCE's APIs to actually scale up your cluster, but the core logic is reusable, and you could plug it into any other system to scale a cluster elsewhere. And we think that this is a great model for how we can enable people to run on Google Container Engine, but feel like they have the ability to run their cluster anywhere else as well. So running Kubernetes in production often means you have multiple teams that need different levels of access to your cluster. It also means running development, testing, staging environments so you can validate your code changes before you push them to production. And in Google Container Engine, you can leverage the power of Google IAM and Kubernetes namespaces to make sure that the right people have the right access to your cluster. So Kubernetes namespaces divide your cluster up into logical subdomains. And each of these logical subdomains has different levels of access control, has its own DNS hierarchy, so you can easily segregate services. And you can use namespaces for whatever you'd like. You can create a namespace for every user in your department. You can create a namespace for every app that you deploy. And you can use namespaces for different environments. So you can have a testing namespace and a staging namespace. They're quite flexible, and it allows you to easily segregate different parts of your application. One thing that we do recommend is using a separate cluster for your production instances, because although namespaces are a great logical boundary, they are not a very firm boundary in terms of isolation, either for security or for interpod utilization. And with Kubernetes 1.6 coming out soon, you can use role-based access controls to bind IAM roles to permissions inside of a namespace, which allows you to create very fine-grained controls of who can access resources within different namespaces in a single cluster. So Google, we're really proud of the load balancing products that we offer as part of the cloud platform. Our load balancing is built on the same front-end serving infrastructure that powers services with billions of users, like Google Search, Google Maps, Gmail, and YouTube. With Google Container Engine, your application can also take advantage of these amazing capabilities, just like Niantic did when they were building Pokemon Go. Google Container Engine offers 2 levels of load balancing. The first is level 4 load balancing. Level 4 load balancing is appropriate if you need to terminate TCP connections or if you need to handle raw UDP packets. Level 4 load balancing sends your traffic to what we call a service. A service in Kubernetes is a group of pods that provide a stable IP. And one thing you'll know if you want to run containers that can get rescheduled is that containers can move around inside your cluster. And so by using a service, you know that your traffic will always get to your pods, even if those pods have been relocated onto new VMs. External services are then exposed with an IP address. By default, services are internal and not exposed to the internet, but it's quite easy to expose them. And on Google Container Engine, this is done with a cloud network load balancer. The other type of service that we use is called an L7 service. So many applications that are built today are built on top of sort of the web foundational standards of HTTP and HTTPS. We have an object in Kubernetes called an ingress object that makes it very easy for you to configure this L7 load balancer. And the power of the L7 load balancer is that with a single exposed IP address and port or domain name, you can easily map traffic to multiple services in your cluster. So you could map some traffic to a static content service that is serving static web pages that have been pre-generated. And you can map other parts of your URL paths to dynamic content, if you need to talk to a database. And all this can be expressed within an object that is then declaratively applied to your cluster and then instantiated in terms of a Google Cloud L7 load balancer. With that, we're going to switch over and do a quick demo. Excellent. So for this demo, I've pre-provisioned 2 clusters in 2 different regions. So there's one cluster that's in the US West 1 region and one cluster that's in the Europe West 1 region. And what I'm going to show you is how easy it is to deploy an application onto Google Container Engine and get it up and running and serving real traffic to end users. So the first thing that we are going to do is this application is going to use Cloud Spanner, which is a newly announced part of Google Compute Engine. And Cloud Spanner is a global database that has strong support for transactions. It turns out to talk to Cloud Spanner, the identity model requires you to use a service account. So what we're going to do is we're going to create something called a secret in Kubernetes that encapsulates the client-side credentials of that service account to allow us access to Cloud Spanner. Now, I haven't mentioned secrets yet, but what secrets do is that secrets decouple the sort of sensitive information of your application, such as passwords or private keys, from the actual configuration of your application. And this is great because the configuration of your application, you generally want to put in source control, especially if you're running in production, because that makes it easier for you to version and to share among multiple people. But you really don't want to check your passwords into source control. I know we've probably all seen, people will do a search of GitHub and find all sorts of passwords on GitHub, which is not really a best practice. So secrets allow you to separate those two pieces of data. So the next thing we're going to do is we're going to create a deployment. Deployment is a higher level controller that creates pods for you. Generally, you don't want to create pods by yourself because a pod has a limited lifetime. If a pod dies, it will not be recreated. But if you create a higher level controller like a deployment, the deployment is then responsible for making sure that the pod is always running. So in this case, we've created a deployment with a single replica, which is going to launch a single pod for us. And in the deployment specification, there are lots of different fields. Most of them are not actually very important. This one's pretty important. This tells us which container we're actually going to run. This deployment has a single container. And then this container is parameterized by a few environment variables. So through the environment, we're going to tell it where to connect to, like which Spanner database instance we're going to connect to. And then we're also going to tell it where to get the credentials to connect to that database. So we just created a secret. That secret is automatically mounted by Kubernetes inside of the pod at this location. And then the code will read the secret from that location and connect to Spanner. Caps lock. There we go. So if we then look at our pods in the cluster, we'll see that we have a single pod, and it's now in the running state. So while we were inspecting the YAML file, the scheduler took that deployment, turned it into pods, found a place to run the pod, and the system then fetched that container image from Google Container Registry, instantiated it, and now it's running. So that's great. So next what we're going to do is we're going to create a service. So in this case, the service that we're creating is a service with an external load balancer. What this external load balancer will do, as I explained before, is it will actually talk to the Google Cloud APIs and create a load balancer for you that will expose your service to the internet. If you leave this last line off, you will create a service that is only accessible inside of your cluster. If we list services, you can see that the Kubernetes service is a default service that's provided with your cluster. And the service we just created is called Next. The external IP takes about a minute or so to show up. And once that IP shows up, we'll be able to go ahead and look at that service in the web browser and see and load our web page. So while we're waiting for that, we will go back and look at our networking tab in the Cloud Console. And if we look at load balancing, we should see, here's our service. So our service is now being provisioned by the system. So this is done automatically for you. You just tell Kubernetes, I'd like a service externalized. It goes ahead and programs that for you. And there it goes. So now we have an external IP address. So we'll go ahead and load that. Aha, there we go. Great. So our pod is serving a simple web page. It tells us the name of the pod. So we can actually go back and verify GT1T5. Great, looks like it's matched up, and it's telling us the region that it's running in. Now our pod is pretty simple. It serves us data, but it also writes an event into Spanner. And so if we go into the Cloud Console, we can actually load up Spanner, and we can find the database that we provisioned. And we can actually search in the database and say, okay, look, we've got requests. They're all coming in to US West 1. Okay, that's great. So we've got our service. It's been pushed into one cluster. It's externally exposed. If you guys want, you can hit the same IP address, and you'll get the same response back. Each of those responses is now being written to Spanner. So one of the most powerful things about Kubernetes is the way we've deployed this application. It's very easy, but it's also very easy to do it again and again and again. And so in this example, we have two clusters in two different regions of the world. And we can apply exactly the same YAML files to our second cluster and get exactly the same results. We can get the same code running, and since it's been parameterized, it will now tell us that it's running in Europe. So to do this, what we're going to do is we're going to switch contexts. So the Kubernetes client command line interface knows how to talk to a single cluster, but it has credentials to talk to multiple clusters. And using contexts, you can actually switch between different clusters that have all been configured. You can pass it on the command line for each command you run, or in this case, we're going to sort of set the global context so we don't have to pass it for each of the commands. The 3 commands I'm copying now are exactly the 3 commands that were previously run. They're just running them now in a different environment. So again, if we get deployments, we see that there's the same name of the deployment. If we actually list the nodes in our cluster, we can now see that we are indeed talking to the Europe cluster, and we're no longer talking to the US West cluster. And if we try to get services, again, we'll see that it's pending. If we run a query here again, so all of our access, it looks like we had a couple that went to Europe West. That's probably from when I was testing prior to the presentation. I forgot to clear out the database. And that's still pending. So we'll give that just a second to come up. We can check on our load balancer again and watch it get created here. So on this page, we've got the single load balancer that was there before, and shortly we will get a second load balancer. OK, there it's coming up. So quite shortly here, we should have another IP address. And there it is. Excellent. And when we load this IP address, instead of saying US West 1, it should tell us now we're running in Europe. And again, it's telling us the name of the pod that is hosting this application. So we can, if we want, scale our replicas out, and we can see the pod name change. So now we see that we've requested there to be 2 replicas. And if we reload the page, we should see it flip between the 2. It may take a second for that to show up. So now we have our service, and it's been deployed into 2 different regions, which is great. We can serve European customers from Europe. We can serve US customers from the US if we'd like, by pointing them to 2 different IP addresses, which we can map to domain names. But most people want us to have sort of a single entry point for all of their customers. And one easy way to do that is you can create a DNS entry, and you can put both of these IP addresses in the DNS entry. That will cause traffic to round robin between the 2 clusters, which is perfectly reasonable. But we think a much better solution is to use Google's global cloud L7 load balancer. The L7 load balancer will automatically push traffic to the 2 clusters based on where the request is coming from. So for this demo, I've pre-provisioned an L7 load balancer. You can see it's configured to point to the 2 clusters, one in Europe West 1 and one in US West 1. And you can actually see that in both cases, all of the backends are healthy. So the backends here are the VMs, the nodes that are part of the cluster. And then if we go look at the traffic, you can see that it turns out we're sending traffic to both of these backends. So before the presentation started, I started a while loop. I should do that more slowly, with a curl command. So I set up a DNS entry that points to my L7 IP address, and just 10 times a second, I'm curling that from my laptop. Now my laptop's on the west coast of the US, and so the majority of the responses here are going to be US West 1, if you watch this line as it toggles. But I set the L7 load balancer so that after getting 5 requests per second to the US, it'll actually spill over traffic to Europe. So what this means is that if too many requests are coming in that will overload my set of backends, they'll spill over to the second cluster. And you can see from the terminal output here that every once in a while we are getting responses that are spilling over to Europe. Likewise, if we load the L7 IP address here, for the most part, we will get US West, but every once in a while we'll get Europe because the traffic is spilling over. So this is great. So now we've deployed our application. We've deployed it in multiple regions. We're serving traffic globally. What happens if something goes wrong? So in this case, we've got requests coming in from both places. And we're going to switch back to the US West cluster by changing our context. And we're going to delete our service. So this is simulating what happens if something goes wrong. Now your service no longer exists. Your service is no longer exposed to the internet. If you go to the first IP address that was trying to serve US West 1, it's not going to work anymore, right? So that service IP address is gone. So if you'd set up DNS, you'd have 2 IP addresses that were being round-robined, and about half the time your customers would stop getting responses. And even worse, with DNS propagation delays, if you want to change the DNS entry, it's going to take quite a while before that change gets out to all of your customers, and they actually see the new IP address that they should be going to that's in Europe. But if we look at the L7 balancer, it has automatically failed all of our traffic over to the cluster that is healthy. And all the responses now are coming from Europe. And you can see now that they're bouncing back and forth between the two different pods that we've scaled up to. And there's a little bit of lag in the Cloud Console, but if we refresh this in a second, we'll see that all of the traffic is now overflowing. And it does mark here that all of our backends are unhealthy. And with that, I think we're going to switch back to the slides. So the final area that I'm going to talk about today is portability. As Hen mentioned earlier, we recognize that not everyone has the luxury of running their application in Google's cloud. One of the primary tenets of Kubernetes is that we should have portability across deployment environments. Kubernetes should run great in Google's cloud. It should run great on-premise. It should run great on different operating systems and different hardware architectures. Anywhere you can run containers, you should be able to run Kubernetes to manage those containers for you. Now, it's really easy for someone to stand up on stage and tell you, these platitudes about how easy it should be to run Kubernetes anywhere. But what we want to do is sort of show you through examples of customers. And so Pokey is a company who decided to rebuild their monolithic application using microservices and containers, and they chose to use Kubernetes for their container-centric infrastructure. They launched Kubernetes in their existing environment. They ran it themselves for a little while, and then they decided, it's a lot of work to keep up with updates. It's a lot of work to manage my own cluster. We're going to try out Google Container Engine. And so they switched to Google Container Engine. Now we have a happy customer. But in the process of migrating into Google Container Engine, because all of their applications were written to run on Kubernetes, it gave them the confidence that if they do want to run anywhere else, as long as they can run Kubernetes, they are free to go wherever they'd like. So today, they're a happy customer, but if they get dissatisfied, then they are free to run it on GCE itself without using Google Container Engine or on bare metal or anywhere else they'd like. And the reason that this works is because Kubernetes provides really good extensibility points. Kubernetes can scale down all the way to running on your laptop if you want to run a development environment. Again, we would not recommend that for production, but it's great for testing out your applications before you push them to production. That means you can run your containers while you're on an airplane without having access to the internet. You can also run it on bare metal. You can run it in many different cloud environments. And the API and implementation of Kubernetes is completely open. The whole system is modular, and you can replace different components. And the way that we support different clouds is that we do replace different components. So earlier in the presentation and in the demo, we showed how we can integrate with Google's networking, Google's Cloud Load Balancer, Google's L7 Load Balancer. All of those, when you're integrating with those systems, you're expressing the intent of your application through Kubernetes objects, through services, and through ingress objects. And on GKE, or on Google Container Engine, we then instantiate those objects through Google's APIs. But if you're running elsewhere, you can run a different ingress controller that might instantiate your L7 load balancer using Nginx. Or you might instantiate it, service controller, just using IP tables. So the whole system is modular and replaceable and can run anywhere. And the other nice thing about this is that your applications are not written to depend on any particular infrastructure. Your applications depend upon the Kubernetes APIs, and Kubernetes mediates those APIs with the environment that they're running in. So we've talked about the network models. Another good example of this is volumes. So if you're running on Google's cloud, you're most likely using Google's PDs, Google's persistent disks, which can be mounted into your containers. But if you're running on bare metal, you might instead have persistent volumes that are backed by NFS. And this allows you to easily migrate your application from the legacy deployments into containers and lift and shift onto the cloud when you're ready to migrate. It further means that after that migration, as we saw with Pokey, that you don't feel stuck where you went to, that you still have the flexibility to go wherever you think is the best place for your company. So we like to say this puts your apps on wheels and lets you roll it around wherever you'd like to go. And with that, I'm going to hand it back to Hen.
Thank you, Robert. So we've seen that production changes everything, right? And we talked through some of customer example, how we in Google can help. And I forgot to mention, maybe it's a nice story to tell now about Niantic, right? They started on Kubernetes 1.3, and they had a different specific size of cluster, and they need to scale it up. On the same time, we were releasing a new version of Kubernetes that was supporting 2,000 VMs per cluster. So without disturbing anything, and for us doing all the work for that, we were able to scale them out to a bigger cluster. So we first upgraded the cluster, the control plane, and then the nodes, and they were able to grow to the scale they needed. We saw auto-scaling. We talked about access control, load balancing, and of course, portability. We want to believe that you have a choice, and we want to keep you that choice and have the freedom to make a decision. We commit to be the best, okay? And this is our goal, to make sure that this is the best place for you to run your containerized applications. But all I speak about is about today, right? And again, as I said, when we are making a decision about where to run our production workloads, we want to make sure that we can be confident that this is the right platform or the right decision for us for the future. I really like this quote from Sam because it's able to capture in one quote both the today and the future. And the first thing he mentions is about Kubernetes, right? And why Kubernetes is production ready today and the future. I think one thing to note is about the community. The community has been growing very fast. It's one of the top 10 projects in GitHub from engagement. And looking on the 1,500 contributors, I think more interesting even to say that out of those 43,000 commits, more than 50% of them are actually not done by Googlers. This means that the pace of innovation is mind-blowing. Okay, the new features, the new requirements are really there to make sure that everywhere you take Kubernetes and run your containers, you will have a production-ready system. I also believe that this really raises the bar, right? When we speak about when to release a new version of Kubernetes, we look on all environments, right? And we are making sure that it works well everywhere, and we have users and contributors that are doing the same. What do you say, for example, if you're planning to grow and you want to now hire new professional people to manage your cluster? When you choose Google Container Engine, it's the same as any other Kubernetes deployment from that knowledge perspective. So having 200 meetups around the world allows you to hire those professionals to join the team without the need to train them specifically to your system. And the last thing is that having that modularity, by having different projects based on Kubernetes, you can change your monitoring solution. We talked a lot about the infrastructure, but also the tooling around it. Your DevOps tool chain, your logging, your monitoring, tracing, all of those things can be changed with new things that will come along. So to summarize, Google Container Engine benefits is, first of all, pure upstream Kubernetes. This is the fastest way to get the Kubernetes releases available to you in a reliable manner. We bring our 12 years of experience of managing production systems on containers to you by managing and upgrading your cluster, your control plane, and your VMs. And you get all the benefits and all the goodness of the Google Cloud Platform. You can really focus on your application deployment. Thank you very much.